Hello everyone and welcome to On the Spot STEM. Today we'll be tackling problem number 1 from the USACO 2019 Gold Contest. The problem states that Farmer John has a graph with each node of the graph connected with an edge that is bidirectional, and it has a flow component and a cost component. And we calculate a path from the start to the end. We want to print out the maximum value of the flow divided by the cost. So let's look at what that means for this problem. In this graph, which is the sample test case, we have 1 connected to 2, and the cost of this will be 2, and the flow will be 4. Here, for the next one connecting 2 and 3, the cost will be 5, the flow will be 3. We calculate the total cost as the sum of the cost that it takes to get to 3. That's 2 plus 5, which is 7. And then we calculate the flow as the minimum value of all the flows we encounter. And that's the minimum of 3 and 4. So then we get the value of 3 over 7. And we basically multiply this by 10 to the 6th, and we print out 428,571. So looking at this problem, it definitely seems to be a shortest path graph problem. So a few algorithms like Dijkstra's and Floyd-Warshall come to mind. But then there's this condition of the flow rate where we only pick the minimum flow rate that definitely messes things up for us. So let's look at how we can consider this by adding our own test case, where we add another element that connects 1 to 3 with, say, a cost of 1 and a flow of 2. Here, the optimal path is to connect the 1 and the 3, but at first, this may not seem obvious to us if we're just going based on any algorithm. So how can we choose to tackle this whole flow issue? Well, to start off, we can sort of think about this that we want to maximize the amount of flow because the flow will be on the numerator. So we can try sorting these edges from greatest to least in terms of the flow rate. That gives us this edge will be first, this edge will be second, and this edge will be third. But how does this help us? Well, if we systematically only add edges to our graphs as they appear in greatest order, then we know exactly the flow that we'll be using, and then we can calculate the cost using one of those graph algorithms. Let's look at what this means. So we see that the maximum is the flow rate of 4. So we add that edge to our graph, and that's the flow rate of 4, and it has a cost of 2. Have we made a path between 1 and 3 yet? We have not. So then we add the next flow rate, and that will be the one from 2 to 3 with a cost of 5, and that has a flow rate of 3. So since we know that we are processing the values of edges with flow rates 3 or above, we know that the numerator has to be 3. What we don't know is the cost, but this cost can be solved by using a Dijkstra algorithm, because if we basically calculate the shortest distance from the node that we want to get to, 3, to the node that we're starting at, which is 1, then that's essentially going to be our denominator. And we can see that if we were to do any algorithm on this, this will be 7. But we're not done here. This is one possibility, but we need to process everything. We add the last one, which has a flow rate of 2 and a cost of 1. So we know that since we're processing all edges 2 or more, the numerator has to be 2. And we know it can't be 3 because we already processed the case of 3 in the earlier one. So this will have a numerator of 2, and then let's perform a Dijkstra's algorithm on this graph. Now, if you don't know Dijkstra's algorithm, I'd recommend checking it out on a website like Geeks for Geeks, but here's the abridged version. We start at the node 1, and we look at all the edges coming out of 1, and we take the shortest one. And then we see that that takes us to node 3, so node 3 will be reached in a weight of 1. And then we can process the other ones to get the minimum value. So we know that to get from 1 to 2, it's a cost of 2. But then when we're looking at the one from 2 to 3, we see that we would have taken 5, which is the edge length, plus the amount that it needed to get to 2, which is 2. So 5 plus 2 is 7, and we have already reached 3 in length 1. So 1 is less than 7, so we don't need to actually change this value. and we see that the minimum distance is 1. And from here, we can essentially put a 1 in the denominator, and then this we can see is our maximum, and that is our answer. Let's look at the coding implementation of what we just discussed. So to start off, I've set up a few different things, so let's go over what I've set up already. I've set up the scanner, file, and print writer. Those will be used to read the input and print output. And I've also set up reading in the data that we're given. So I've created a data type called an edge that stores the beginning point, the end point, the cost, which I've labeled as the length, and the flow. And I've made 2 different custom sort algorithms. One to sort based on the length, because this will be used for Dijkstra, and then the other one sorts based on the flow. This will be used to process edges. So now let's look at how we read in the input. We read in the point, and we subtract 1, obviously, because we want to 0 index. We read the length, and we read the cost. And because it's bidirectional, we have to add the edge between A and B, but also the edge between B and A. And finally, I've set up a hash map, and this hash map will store our graph, because we're not adding all the edges at once. We're adding the edges one at a time. So now let's look at how we're going to implement our processing algorithm. So we want to first start off by sorting our edges by the flow length, so we know the order to process them in. So we can run a collections.sort on the array list of edges that we made, and we want to use comp flow, which is how we are going to sort it in increasing or in decreasing order. After we create this, we can use a sort of 2-pointer approach to process them one by one. So let's create a pointer to the front of the array list that we'll call L point, the left pointer. And right now it's pointing at the very beginning, so it's at 0. And then we want to also store our print value, which is equal to 0 right now, because we're going to be storing the maximum value. So now let's create our for loop. I'll use an outer because it's actually going to get a little tricky for the for loop, and we want to start off at the maximum flow value, which is 1,000, and then work our way down to the minimum flow value, which is 1. And the reason we start off at 1,000 is because that's like the maximum value, which means that's what the largest flow rate can be, and that's the largest one we'll have to ever process. And what this for loop is doing is that I gives us a bound to add edges until the flow rate reaches that amount. So let's start adding our edges in. We can create a while loop that states that while the left pointer is less than the size of the array list, this is going to prevent an index out of bounds exception. And we also want the value that we're going to be using to be, we want this to be greater than or equal to I. And then if this condition is met, we want to add this into our graph. So we want to get the point that we just saw, and we want to add the edge. After this is done, then we want to increase our left pointer one more, and then we want to also set k equals to true. So you might be wondering what this boolean is for. Well, we don't want to run any unnecessary amount of Dijkstra's, so we make sure we have a variable that stores if we've actually changed our graph from the previous iteration. And if we have not changed the graph, so if k is false, we want to continue outer. Now it's time to start our Dijkstra's. So what we always want to do is store a Dijkstra array, and this will store the minimum value to get to node n from the beginning. So since we are starting at the beginning, we also want to make sure that we store the beginning value as 0 because it takes a length of 0, a cost of 0 to get from the beginning to the beginning. And we also want to fill the rest of the values in the array with an integer.max value because currently we don't know how much it'll take to get there. We just want to make sure we have a large value that we know will never be reachable through just an actual distance. We're going to be using the priority queue implementation of Dijkstra's because that is really fast. It's n log e for the number of edges that you have. So we're going to store a new priority queue, pq, and we also want to state how we want our priority queue to sort by. So we're going to pass in the length sorter that we already used earlier. After this, we want to add every edge that we need that is connected to 0 because we're starting at 0. And then we want to add that to our priority queue. Now with classic Dijkstra's implementation, we check while the priority queue is not empty, then we take the next edge, and then we also want to check if this is an edge that's not worth taking. We also want to check if this is an edge not worth taking, so we see if the Dijkstra's of where we're going to end up is already less than where we are plus the distance it'll take to reach there. And if that's the case, then we just say continue. However, if that's not the case, then we want to set the value of this to actually equal what we just calculated. And then we want to add all the edges that come out of that node. Now it's redundant to get this, use the edge to go back to where we started from. So we can put a little check condition that if where we're going to go is where we were already at, then we can continue. There's no point to process that. Otherwise, we can just add the edge in. Now, this finishes our Dijkstra implementation. So now all we have to do is check if we ever actually reach the end, because if we never reach the end, there's no point in actually storing it, because there was an incomplete graph. So if we never actually reach the end, then we want to continue out. Finally, if we did reach the end, then we want to actually save that as our maximum value. So we want the integer value of 10 to the 6, so we'll use math.pow 10, 6, multiplied by the double of whatever I is the flow rate, remember, and dji of n minus 1 is the cost. So this is the ratio that we're striving for, and we want to compare it to the value that we currently have. Finally, all we have to do is put a pw.println and close our print writer as always. Now let's actually submit the code that we just created. As you see, the code ran without a hitch and it was under the time limit.